fuels and combustion. Oh, we got pink today. All right. And we have conservation of mass, so we have to apply that to our reaction now, so to balance our equation. We'll look at some of the parameters in combustion analysis. Energy balance is really the big one in this one. And then some of the parameters that come out of that: enthalpy of reaction, enthalpy of combustion, heating values. So like when back in chapter 3, we had combustion efficiency, or chapter 2, sorry, where the energy in the fuel is the heating value. Well, we can actually calculate the heating value in this chapter. And then we have adiabatic flame temperature. We'll kind of cover the entropy change of reacting systems and how the second law looks at that. We won't have any examples from that, but we'll kind of look at that, of what that means. Okay, so fuels, any material that can be burned to release thermal energy. Okay, so most have hydrogen and carbon. So your simplest on the hydrogen side is just pure hydrogen as a fuel, right? If that burns, it becomes water, right? Or the simplest on the carbon side is carbon, like if you thought of like a pure coal, which would be all carbon, then that would combust and be release thermal energy and be to CO2. So 2 weeks from now, according to, so I got a question about the exam. Let's see. So today's the 4th. Let's see. Yeah, sorry, 2 weeks. So next week, yeah. So next week is the we'll do chapter 15, and we have then review, and then the exam. So the exam is on the 18th. Yeah, correct. Okay. Check window here. Okay. All right, so let's get back to lecture. All right, so we have thermal energy. So the most common you hear of is hydrocarbon fuels. So that's a combination of carbon and hydrogen, right? So some number of molecules of carbon, some of hydrogen, and that's your hydrocarbon fuel. Okay. Gasoline, diesel fuel, any of those kind of things you hear are a combination of a lot of different hydrocarbons. So gasoline, we usually say it's octane, but it's really got hundreds of different hydrocarbons in it. Okay, same with diesel fuel. It's got a combination of hundreds different of it. Okay, and how they get this, the different hydrocarbon fuels, is by basically distillation. So they evaporate the fuel and use the evaporation to separate, lighter versus heavier fuel. Okay. And there's different, so with alternative fuels, there's different amount of energy content in the fuels. Okay, so if we look at, say, gasoline, we have 31,850, and this is kilograms per liter. Okay, so they're doing it liter just because of, in transportation, volume is a big thing, because that's how much space it's going to take up, and you got to transport that space when you're moving that fuel. But that's the energy in gasoline, and we have a whole bunch of different fuels that are being shown here, and they're using this other column to show an equivalency. So, one where is equivalent to it, where you see there's a little bit more in diesel fuel of the energy content, so it doesn't require as much space before. Or if you look at, say, ethanol, if you had a pure ethanol, you need a little bit more space, or methanol, a lot more, or compressed natural gas, a lot more, to get the same amount of energy content. Okay, because if you look at the energy that's released when it combusts per unit of volume, you see that it's a lot less. Okay. All right. So when we have a fuel, we need an oxidizer to burn that right? So we take that fuel and have the oxidizer, and we use air. Why do you think that is?
There's a lot of it.
Yeah, so it's easiest to use, right? There's a lot of it, right? So if we wanted to use just oxygen, we would have to remove the nitrogen from the air, really, to use that, right? Or so that becomes the reason of using air, right? And when we look at what's in air, we typically approximate the air as just oxygen and nitrogen, right? But there is other things in the air where the third quantity is actually argon, is the next in what's in air, and then CO2, helium, neon, hydrogen in air. There's other things too, but we will simplify this to air in most of our analysis of just being dry air, which is 21% O2 and 79% N2. Okay, and since oxygen is our oxidizer, excuse me, we will even convert this to make this even easier on us than using 0.21 instead of 0.21 O2. We'll do it as 1 kilomole of oxygen in 3.76 N2, which means there's 7.6 kilomoles of air. So where does this come from? If you take 1 and divide by 4.76, this is going to be 0.21. Okay, and then if you take 3.76 and divide it by 4.76, you're going to get 0.79. If I can write a 7. Okay. Okay, so that's your 21%, 79%. But we're just looking at, since oxygen is the oxidizer, we just want it easier on our balance equation. So we look at it as 1 kilomole. Okay. Okay, so that's what this comes from. So that's also, and when we get into the equations, this is also one of the most common mistakes. There is 4.7 kilomoles of air when you're thinking about when you're looking at a balance reaction with 1 kilomole of oxygen, because you still have nitrogen kind of going along for the ride, right? Okay, combustion, a chemical reaction, which fuels oxidize and energy is released. All right, for combustion to occur, there's actually an ignition temperature, okay? So we have to get this fuel to a certain temperature before it will even ignite, okay? So there's a temperature, and it's different fuels require different temperatures, okay? So gasoline is about 260 degrees Celsius, carbon 400, hydrogen 580, carbon monoxide, because carbon monoxide can still burn can still go to CO2. Okay, you put some oxygen in it. All right, so it needs 610. We have methane 630. Okay, so that plays a role in say in engines, compression ratios, or how you ignite an combustion, whether it's with a spark or what have you, of how you're going to ignite this fuel now. Okay. The other thing that happens is that's just the temperature part of it. There's a amount of fuel and air that's required for a combustion. Okay, so and that depends upon the fuel again. So here it's showing you natural gas does not burn in air in concentrations less than 5% or greater than 15. So you need the right amount of proportions of air and fuel for it to even burn, right? If you're too much air, you're basically, you won't sustain a flame. If you have too much fuel, you won't sustain a flame and combust. Okay. And if we think of a reaction chamber right here, so this would be our boundary. We have some reactants, maybe it's a fuel and it's air, and they come in, the reaction occurs, you have products, right? So maybe there's some heat leaving our boundary. Okay. When we talk about now in a chemical reaction, conservation of mass still holds, okay, right? And the mass is still conserved, right? If we had 2 kilograms of hydrogen, 16 kilograms of oxygen, you're going to get 18 kilograms of water in that reaction, okay? So when we break it up and kind of balance the reaction by looking at, oh, there's 2 hydrogens on the left and 2 hydrogens on the right, we're basically doing the conservation of mass when we do that, okay? Same with trying to balance the oxygens on the left. There's 1 on the left because of that half times 2. That means there's 1 on the right. And we're basically doing a conservation of mass because we're separating the hydrogen and oxygens, which each have their own molecular weight, and we're conserving it. And we'll talk about that later. So we're doing conservation of mass there, okay? But when you have a reaction, the moles are not conserved, okay? So when we did chapter 13, we set up that table for a mixture, right? And we utilized that the moles were kind of conserved a little bit because we would look at it. So we can only look at the mixture and kind of look at the properties of the mixture, where we could look at it as reactants and look at what that mixture is. And then we would have to look at the products and look at what that mixture is. But when we look at this, you see 2 moles on the left, there's 1 and 1, and there's only 1 mole on the right. So when you have a reaction, moles are not conserved, but mass is still conserved, right? You would still get the same mass from the reactants to the products. All right, so now some of the things we use to quantify is with that, having that right portion of fuel to air is the air to fuel ratio, okay? So that's the most common thing to use to figure out whether you're in that right range or trying to set that range of air to fuel that you need for combustion. So on an air to fuel ratio is on a mass basis. You have your mass of air over mass of fuel. Fuel to air ratio is just the reciprocal. That would be fuel to air would just be mass of fuel over mass of air, okay? If we're using moles, kind of looking at balancing our chemical reaction, and need to get our mass of air and mass of fuel, we get there with our moles and then our molar mass, okay? Will get us our mass, okay? So that one, and we'll have to pay attention again, because this plays a big role in air, is typically the mass that people mess up, amount of mass of air, because of that 4.76 I talked about right here, okay? All right, so if we look at here, we have our reactants on the left and our products on the right. In our fuel to air ratio, we can, we already have, it's showing 1 kilogram of fuel and 17 kilograms of air. So our air to fuel ratio will just be 17 kilograms of air over 1 kilogram of fuel. Okay, so we have 17 kilograms of air over kilograms of fuel. Let's put this in full screen. All right, so here's a balance and a quick example of a balance, right? We have 1 kilomole octane, okay? So that's C8H18, burned with air, and the air contains 20 kilomoles of O2, as shown in a figure. That's right. Assuming basically they're telling us the products are only going to contain CO2, water, oxygen, and nitrogen, determine the mole number of each gas in the products and the air to fuel ratio, okay? So we set up our balance equation right here. So here's our fuel. It has 1 kilomole in front of it, right, as was given. We have this is air. All this is air. That's our 4.76 N2 or 4.76 kilomoles of air is what's in that parentheses, okay? Because there's 1 of oxygen here and 3.76 of nitrogen, okay? But they tell us there's 20 kilomoles of O2, okay? So that's where we put the 20 in the front, okay? So if we multiply it out, you see that there's 20 O2, but there's still all that nitrogen too, all right? Now our products are CO2, water, oxygen, and nitrogen they gave us, okay? So if we look at this, right, we see we have carbons, we have hydrogens, we have oxygens, and nitrogen as what we can set up and put our individual balances. And by separating this, we are actually doing a mass balance, okay? Even though we're going to balance the moles here, but by separating it to carbon, hydrogen, oxygen, nitrogen, that actually ends up being a mass balance because we are taking and separating it. And if you think of the separation of carbon, if you look at that mass is moles times the molar weight, well, we're only looking at carbon, which has the same molar weight. If we're looking at balancing moles, we take moles times that. It's going to give us mass. So by separating this out, we are basically doing a mass balance because we are balancing everything at the same molecular weight, okay? All right. So let's look at this. We have carbon. There's 8 for carbon on the left, and we only have carbon in this balance. There's no carbon monoxide. We only have a single carbon on the X times that single carbon on the right. So that ends up giving us our first unknown, X being 8. Okay. Hydrogens, we have 18 times 1 on the left. Okay. And then on the right, we have our 2 times Y. Okay. So that gives us our second unknown of Y. Oxygen, we have oxygen balance is usually the most number of terms. Okay. So we have 2 times 20. Okay. On the left. Then on the right, we have 2 times X. Okay, we have Y times the 1, right? We have 2 times Z. And we already solved X and Y, so the only unknown is Z, so we get our Z, so our leftover of oxygen on the right. Okay? And then nitrogen, we have 20 times 2 times 3.76, although that's the way I usually do it, but here they're doing a balance of N2, okay? So they just say 20 times 3.76 because they have N2 on the right. They're basically balancing N2, not N, okay? So we have 20 times 3.76 on the left, and then just W because they're, again, balancing N2 and not N, okay? I usually like to do N just to keep it all consistent, but it all works out no matter whichever way you go. And so we get W is 3 of 75.2. You see how high nitrogen, because there's so much nitrogen in the air, so you end up having most of your products is still nitrogen, right? So if we reset this up and substitute in all our unknowns that we solve for, we have this, okay? If now we want to set up the air to fuel ratio, we have the mass of air over the mass of fuel, right? Okay. So if we now, we dealt with moles up here, okay? So we need to use moles times our molar mass of air, moles, molar, so fuel, they did it with carbon and hydrogen. You could do it for the whole thing, like in the back of the book. It will have the molecular weight of octane, or you can calculate it. You know, this is just the molecular weight. They're basically calculating on the bottom for you, right? Since there's 1 kilomole of this whole thing, we just have 8 carbons times 12 as our molecular weight of carbon, plus 18, or they're doing 9, so half is 2 for H2 times 9. So, but you could set this up and just do the molecular weight of our C8 H18, which would have just been 8 times 12 plus, 1, or sorry, let's do, let me set it up the same way. That's times, plus isn't easy to see, so plus R18 times 1, right? And that would just be the molecular weight of C8H18, okay? And they're doing that basically all here by separating it out. Okay, so that's on the bottom. Okay, so they plug in everything. They have it here for the fuel. Now the oxygen, the air side is where I see the mistakes, right? Well, we have 20 here. Okay, so that's our 20. But then you have this 4.76. This is the most common thing that's left off when students do this problem, because you have the 1 right here and the 3.76. So there's 4.76 in those brackets of kilomoles. Okay, and then you have the molecular weight of that air, because air is oxygen and nitrogen combination. Okay, so that's the most common mistake, is that numerator right there. Understanding that, not leaving out everything. Okay. Okay, so we solve and we get 24.2 kilograms of air per kilogram of fuel. So that's our air to fuel ratio. The other thing I wanted to just mention with this problem is you see all these moles in front of these. If we sum this up, all these moles, that would be the moles, the total number of moles of this kind of mixture right here, right? So if we sum this, that's the number of moles in the products. If we took the number of moles of H2O over the number of moles of the products, that would be the mole fraction of water, okay? Which also, we could relate that to our partial pressure. So if you had the pressure of water over our total pressure, let's say that's 1 atmosphere is our total pressure, would be the same as NH2O over the N of the products. Okay, so that would be the sum of all 8, 9, 7.5, 75.2 would be these number of moles in the products. 9 would be number of moles of water. If we had our products, our exhaust, let's say it's the tailpipe of your car, so the total pressure would be, let's say 1 atmosphere, 100 kPa, let's say. Then we could utilize this equation to solve for the pressure of the water. Well, that gives us, if we have basically that's the partial pressure of the water there, we could use that to get dew point from chapter 14. So this, just right here, this analysis brought in chapter 13, our new chapter, chapter 15, and chapter 14 all together to see. So what that dew point, right, the dew point is Tsat at vapor pressure, right? That would tell us when water would condense, right? If it's so cold in the morning, where you would see, like a cloud coming out of your tailpipe of water, that's because, or water dripping out of your tailpipe, that's because it's cold enough that dew is forming and dropping out based upon the fraction of water you have. Or when you see water vapor coming out of a power plant's exhaust stack, that's because it's forming that dew. Okay. So that little nugget of knowledge brought in multiple chapters at the same time. So it's not where you can think, if you can think about how each of the chapters work together, it's not really like a separate thing. All right, so let's bring in some more details about combustion. All right, so if we think about some of these theoretical and actual combustion, complete combustion, okay, or stoichiometric combustion is the other thing that this is called. It's where all the carbon goes to CO2. All the hydrogen goes to water. Okay, that means there's no carbon monoxide, no CO, no just hydrogen. If you're burning any hydrogen, there's no hydrogen in your products. Any sulfur burns to SO2, so there's less and less sulfur. We have more and more regulations where the fuel suppliers got to keep lowering the amount of sulfur in the fuel because basically all that sulfur just ends up as SO2. You have sulfur in your fuel. Incomplete combustion. So if it's not complete, you see all those things that end up being there. You get, some unburned fuel. Okay, so you could have carbon, hydrogen, CO, OH. Okay. The reasons for incomplete combustion, there's insufficient oxygen. Okay, so any of the fuel molecules have to find oxygen. So even though there might be oxygen, there might be enough oxygen for it to combust, they have to find all those fuel molecules have to find each other. So that might play into a little bit of, not having enough oxygen and mixing. So together those things can play a role, right? Because, even though you have enough oxygen in that mixture, they might be on one side is the fuel and the other side is the air, and they have to mix to find each other, right? So there's just not enough oxygen and not enough mixing, okay? Because there's a certain amount of time that you're only letting that fuel and air combust in your combustion chamber. The other is dissociation. So what that is if you get high enough temperatures, molecules just start breaking apart. So let's say N2 will just break apart to 2N. It'll just dissociate into 2N. Okay, so that's just because it's at higher temperatures, it breaks those bonds and it disassociates. So that happens to a lot of different molecules. So that can then create incomplete combustion. Okay. So this is a simplification of complete combustion, of balancing the reaction of if you have N carbons, you get that in the CO2, M hydrogens, then you get M/2 water. The excess oxygen, you get nitrogen. Okay. Oxygen, so there's a tendency of where reactions occur. So oxygen has a tendency to combine with hydrogen more so than carbon. So then normally the hydrogen burns to completion, so you get water, but you got to wait on the carbon. It may get to carbon monoxide, but then it may take time to get to carbon dioxide. Okay, where the tendency of oxygen will combine really quickly with the hydrogen, you get H2O. All right, so stoichiometric and theoretical amount of air. So here's where we start. This slide tells us, and it has a lot of terms to it, but it tells us about the portion of air we're providing to the fuel. Okay, stoichiometric or theoretical amount is the kind of, we're putting in the exact amount for complete combustion of the fuel. So we're putting just the right amount that we can have all the fuel burn to, so if you have all the carbon in the fuel burn to CO2, so we're giving it just enough to get all the oxygen, just enough air so that all the oxygen ends up in CO2 water, okay, and then you have nitrogen along the right. So it's the exact amount, not less, not more, just the right amount to have all that fuel burned to completion to CO2 and water. Okay, so if you had just carbon fuel, it'd be all the CO2. If you had just hydrogen, it'd be all the water. If you have a hydrocarbon, which is a combination of the two, then you get it all burned to carbon and water, right? So that is stoichiometric, okay, or theoretical amount of air, okay? stoichiometric combustion is just then you're having combustion. It's burned completely. Okay, so completely is just CO2, water, and then obviously nitrogen, because you have nitrogen air. So nitrogen belongs to that ride. All right, so now if you have excess air, now you're giving that fuel a little bit more air. So you have, you're giving it more just to make sure all that fuel finds air. Okay, so that's now you're giving more than you need. Okay, more than that stoichiometric or theoretical amount. Okay, so that means that you're going to have excess. Okay, or this could be termed as percent excess of air or percent theoretical air. Okay, so now in this one you'll have CO2, you'll have H2O, you'll have your N2, but now because you have more oxygen than you need in the products, you would have some excess oxygen also. All right, so that's the excess. Now if you have less than you need, you have a deficiency of air. Okay, so that's less than that stoichiometric. Remember, the stoichiometric is the perfect amount, right? So this is our perfect amount. Okay, deficiency is now we're not giving it enough oxygen. So it has, more fuel than air. So you're going to be left with, you could be left with fuel in your products. You could be left with CO, so you might have CO2, but you can't get it all the CO2. You could have just CO because you don't have enough oxygen to get the O2 and carbon dioxide. You just have the O in carbon monoxide. So that's why you'll get higher amounts of carbon monoxide when you don't have enough oxygen. Okay. You might have hydrogen in the products, and then obviously you'll have N2, but you won't really have oxygen in the products because you don't have enough oxygen there to even burn all the fuel. Okay, and then you could have the fuels there too, so that your hydrocarbon in your products also. All right, so a term that normalizes your air to fuel ratio is the equivalence ratio. Okay, and that's just taking your fuel to air ratio actual and dividing it by your fuel to air ratio stoichiometric. So your fuel air ratio stoichiometric, that's the perfect amount, and then your actual is this. So what that's doing is just normalizing it to that perfect amount, right? And that tells you whether if you have a equivalence ratio that is greater than 1, you're basically saying you have too much fuel. Less than 1, you have too much air, which is lean, and then too much fuel is rich, it's called. Okay. All right, if we look at some of these terms and just kind of throw some numbers in them. If we have 50% excess air, so that's where we're putting in 50% more than we need, then that means we have 150% theoretical air. 100%, if it was 100% theoretical air, that would just be stoichiometric. Okay, but 150 means we have 50% excess, right? Or 200% excess air means we're at 300% theoretical air. Again, 100% theoretical air is the stoichiometric. Okay. So if we have these couple examples here, here's methane, combusting, and it's all burning to CO2, water, and nitrogen. So that means this is our stoichiometric right here. So this is stoichiometric combustion. Okay, because all the products, there's no unburned fuel in the products, only carbon dioxide, water, and nitrogen. Okay, so no excess oxygen in the products. And that's what you see here. So this is our stoichiometric, right? All right. If we assumed the composition of our products is complete, so that means, let's say we had stoichiometric combustion, then we can predict what we'll get as CO2, water, and nitrogen, right, for our fuel. We can predict just on the chemical reaction what we would get, and then that could tell us how much, for that fuel, how much carbon dioxide we're producing, right? When we start talking about actual combustion, though, what people do, and if you're talking about an engine manufacturer or a gas turbine manufacturer, they have to meet certain emission standards for that fuel, for that engine, whether it's a gas turbine engine, internal combustion engine. So they actually measure what's in the products, okay? And that's some of what I do in my research, is measuring the products, right? So you measure to see what's ending up in the products, because to see what's actually happening in the combustion process versus what you're kind of predicting to be the composition. Okay. They're talking about an ORSAT, which is a simple one. I've never seen one other than in pictures. Most gas analyzers these days are, more kind of electronic kind of measurement than the method they show with this ORSAT. But there's many different analyzers out there to measure CO2, water. You can measure, any of the other products, carbon dioxide. I already said CO2, but carbon monoxide, hydrocarbons, oxides of nitrogen, all these different ones at different levels of accuracy. So some of them can get up to like 30 grand, 50 grand for just measuring one type of a exhaust emission, so like a NOx analyzer for emission standards testing. So testing for it to report to the EPA for engine manufacturers is about 30 grand. Okay, just for the measurement of NOx. Okay, CO and CO2 is usually a little cheaper because of the technique that's accurate. So that might be, let's say, 15 grand. Okay, and then you need something for hydrocarbon. You need a whole bunch of other ones. So, usually it's just for the emissions. That's not including particulate. That could be like 250K just for the instrumentation of those. So if you're doing particulate matter, so PM, that might be another, 250 to 500K just for that one, because you need a clean room for the, you basically measure filters, because you pass the exhaust sample through a filter, and you measure that filter before and after the experiment. You got to keep it very standard conditions. So it's a very expensive thing to measure accurately, and for reporting to the EPA for emission standards to be had. So then, these kind of things at an engine manufacturer, that they'll have many different engine bays with these, so they can measure it for all their engines, do their R&D. So they have all kinds of engine bays that have all this instrumentations in it.
Whoa.
Yeah. So it's an expensive thing. So that's why there's not too many, and anybody in the university world doing research in engines has typically done it for a while, because it takes that much time to build up the instrumentation, and with the amount of money it costs to have all that instrumentation.
Does UNF have any of that?
I have NOx, so I kind of, because that's one of the big ones. I more look at, have NOx, and then I have stuff where looking inside the combustion chamber. Okay, so PM, that's a tough one, just because if you're trying to do it for EPA standards, especially tough, because you need a clean room. There's A little less if you want to look at just research-based, you can be a little less accurate and use an instrument that's maybe 100K. But I more look at NOx because CO2, for EPA standards, you need to measure it directly. But if I'm looking at diesel, CO is usually not really a concern. You still, if you're reporting it for EPA, you would need to do that. But for research, you don't have to report everything. But for, say, CO2, for research purposes, you can usually just calculate that because it's usually what your carbon in the fuel is. So I kind of look at it more as a research endeavor in my stuff, and looking at NOx because that's that one you have to measure and you can't really predict. Okay, where when I was at West Virginia University, and I still do some research with them, they have cells, because that's they have equipment that can report results to EPA, and I did projects for that when I was there, where their equipment, they have a clean room where you have to put on the whole white suit and booties and all that to measure the filters before and after your experiments. So it's very controlled for that. For that though, if we had somebody wanting to do EPA measurements to report results, that was about 10 to 20K per day for someone to use our lab. Like if a fuel supplier wanted to experiment, it's about 10 to 20K per day. Or let's say Mack Trucks or Volvo wanted to test their engine in an independent lab, not their lab, to see whether their results were good, then it's 10 to 20K per day for them to for us to run the experiments that are at EPA level, okay, because of all that stuff to operate.
Man, that's insane.
Yep, it's an expensive thing. So most on research, when you're looking at research, you don't usually have to go to that level. But when you're looking at for reporting for like the EPA, you have to make sure everything is very accurate, and that you're not reporting the number 5, but it's really 4.5, right? You have an error that you're not accounting for or didn't see because you didn't do the calibrations right, or all the things that require that number to be true, right? Because you're comparing your number to all the numbers that the EPA has for different engines and all that. So it has to have that accuracy to it, okay? That tracking. All right. So enthalpy of formation and enthalpy of combustion. So this is where we start talking about, we kind of had more of a general of the moles looking at, right, and how much air and fuel. Now we kind of start looking at what this means in terms of conservation of energy in some of the enthalpy terms that we have. So we've talked about in our examples so far, we've had sensible enthalpy. So that's the change in enthalpy, the sensible energy, change in enthalpy that kind of changes temperature, right? So that kind of idea, think of when we're in the superheated phase, or like in the compressed liquid phase, or that's kind of that sensible energy part. We've talked about the latent energy. That's our changing of phase, right? For going from a liquid to a vapor. We also have it from going to a solid to a liquid. We have latent energy, right? Changing of phase. Okay. In this chapter, we bring in the chemical energy, right? So we're breaking the chemical bonds when we have combustion, and then energy is released. When you break that chemical bond, we release energy as sensible energy from that molecule. Okay, so we see we don't get to nuclear energy, but that's another form that's inside there, right? So we've had the change in energy of our system. We've dealt with just the change in energy of our state. So that was our latent, and our sensible was all in that state. Now we have this chemical energy that we have to include, okay, in our change in energy of our system now, because that energy is being released. So we have to account for that, okay? So that's the new part in our chapter. Also, well, you'll see it in a minute. All right, so more terms. Everyone loves more definitions, right? We have the enthalpy of the reaction. All right, so that is the difference, basically just the difference of the enthalpy of the products and the enthalpy of the reactants. So if you take sum up all the enthalpy, so that's the total enthalpy of the products and the total enthalpy of the reactants, and get the difference, you have the enthalpy of the reaction, okay? If you have the enthalpy of combustion, again, enthalpy, this is just the enthalpy reaction for a combustion process. So this didn't have to be combustion, right? It's just any reaction. So it could have been an endothermic reaction where it's not releasing energy, it's taking energy, right? That's an enthalpy, that's a reaction. Didn't say anything about a fuel being combusted. But enthalpy of combustion is just the enthalpy of reaction for a combustion process, okay? So if we take, basically we're looking at the amount of heat released, and we're burning, to a standard amount, 1 kilomole or 1 kilogram of fuel at some given temperature and pressure, okay? So these are very much related, right? But slightly different, right? Enthalpy of formation is the energy absorbed or released when a component is formed by stable elements. Okay, so that's the important part, is the stable elements. So when we talk about that, that means stable elements means if it's formed from just oxygen, nitrogen, hydrogen, carbon. Okay, and what is that energy absorbed or released for that component? Okay, so all right, so some examples. Here is our enthalpy of reaction, okay? Okay, we have the enthalpy, the total enthalpy of the products. So we took each enthalpy of each component, like maybe CO2, and multiplied it times its moles, and summed up all the different ones of it. That gets summed them all up of the products, you get the enthalpy of the products. Subtract off the reactants, and you get this, okay? This happens to also be the enthalpy of combustion, because this is a reaction, but it's also a combustion reaction. So that means we end up having the enthalpy of combustion equal to the enthalpy reaction, because it's an exothermic reaction of combustion and not just a reaction that could be endothermic for that. All right, so we have our enthalpy of combustion. Okay. All right, so here you're seeing it. We have our combustion chamber is our boundary. Okay. We have carbon going in, we have oxygen going in. Those are our stable elements, right? Carbon and oxygen are the stable elements, and it's forming CO2. Okay, they're coming in at 25 degrees Celsius, 1 atmosphere, and we're waiting. The exit is also coming out at 25 and 1 atmosphere, and we have our heat that's being released from our chambers. So that's why you see negative, because heat's going out, right? So that ends up also being our enthalpy of formation for this reaction, because it's being formed by stable elements. All right, so it's again the same process, but it's showing you just on one slide where we're taking our stable elements of carbon and oxygen and producing CO2. We're coming in at the temperature, standard temperature, and leaving at the standard temperature. And if you do that, all that heat that comes out of that when we produce CO2 is this value, okay? And for CO2, that ends up being the enthalpy of the reaction is equal to the enthalpy of combustion, okay? which is also the enthalpy of formation in this case, because it's again from stable elements. So it's a nice, so how we signify the enthalpy of formation is this HF, subscript F, and then this degree symbol tells us it's at standard conditions. So it's at pressure of 1 atmosphere, temperature of 25 degrees Celsius. All right, so heating value. Okay, so that's that energy in the fuel that we talk about. So the heating value is the heat released, fuels burn completely, right? When we return, basically, it's the enthalpy of combustion or of a fuel, okay, the absolute value, because we just give it as a positive value, so that's why. But let's look at this example here. We have our combustion chamber. We have our reactants going in, right? We're at probably 1 atmosphere here. Temperature is 25 degrees Celsius. Fuel and air is going in. We have our products coming out, okay, of, it'll have, if you're burning a fuel, it'll have CO2, water, nitrogen, okay, and the heat that we get out is going to be our lower heating value in this case if we have water as a vapor, okay? If we say water is a liquid in the products, then there's a little bit more heat that gets released. If you think of your dome, okay, as you go from here to here, right, from saturated vapor to saturated liquid, you're releasing more heat to condense. Okay, so that means that's the higher heating value, because you get more heat released if your products is water, if water is liquid. Okay, if it's vapor, then it's there's less heat release. So that's why there's these two. There's the higher heating value of the fuel, lower heating value. Higher heating value is water's in the products is a liquid. Lower heating, it's a vapor. When we talk about combustion in internal combustion engines, like a car, you're typically using lower heating value, because what's coming out in your tailpipe, water is a vapor. It's not a liquid, so we don't use the higher heating value. You use the lower heating value. When you look at, say, fuel cells, like a hydrogen fuel cell, they'll use a higher heating value, because hydrogen, it goes to liquid water, it's operating at these lower temperatures. So when they're using the heating value, they use the higher heating value, because the products theirs is water, okay, in those reactions.
So I'm having trouble understanding that. So if the reactant is in a liquid form, that would mean that we extracted more heat from?
It's more the products. Okay, so if we ended up with water as a vapor in the products, it's right here, right? So if we let it get down and had our combustion chamber where we let water become a liquid, so here instead in the products, so it exits here as a liquid, that means there was this amount of heat that was also released from just that water, the latent energy. Okay, there would be that much more that's released here. Okay, and that would make it the higher heating value, not the lower heating value. Okay, make sense?
Yeah, I think so. Thank you.
Okay, so yeah, it's lower heating value, or if you release that energy, that latent energy, then from the water, you get the higher heating value. Okay. So a bomb calorimeter is what's used to kind of get these standard heating values. So I think I have a picture up on Canvas or a video. I can't remember which one it is, or you can search this, a bomb calorimeter. They're just, burning a known amount of fuel and usually have a chamber of water around it and measure the increase in water temperature, because the heat from the combustion reaction in the bomb calorimeter goes into the water. So they'll measure the temperature change of the water to basically measure the heat released by the reaction chamber, because it's easier to measure that water, and how much temperature increase you get in that water is due to the heat being released from the combustion, the bomb calorimeter, the combustion. All right, so here is a enthalpy of combustion. Okay, so in this case we have octane. Okay, so liquid octane. The other key thing is everything is at 25 degrees Celsius in 1 atmosphere. So we haven't really talked about sensible energy change, right? This is all reaction, the chemical reaction change, the chemical energy change that we're still talking about, because everything's at the same temperature in and out, okay, and pressure in and out. Okay, so if we have this octane, we set up our balance equation. We could separate carbons. We see 8 here, so that'll get us 8 here. Hydrogens, you have 18 here. You have divide by 2, so you get 9 times 2 is 18. Okay, and then you can use that and solve for your A theoretical here, right? And that'll be over here too. But they don't necessarily in this one need it. You'll see. So enthalpy of combustion, it's just the enthalpy of the products minus the reactants. Well, products are all these. Okay. So we have CO2, water, nitrogen. Okay. So we have CO2, water, and they're not showing the nitrogen, right? And I'll get to that in a second. And then on the reactants, we have, our octane, we have oxygen, we have nitrogen, but we're only showing the fuel, okay? So this is our reactants, and this is our products. And that's because the enthalpy of formation, because these are stable nitrogen, the enthalpy of formation is 0, okay? So HF, and you can find this in your back tables. So in table A26, it'll just show 0 for N2. Okay, so enthalpy of formation is 0. So again, it's 0 here, because that's nitrogen on that side. Oxygen is also a stable element, so that's also 0. Okay, so that's why you don't see oxygen and nitrogen, or in the products nitrogen. That's all because you're at 25 degrees Celsius in 1 atmosphere. Okay, so then it's just CO2, your products, water, reactants, octane. But you could also put in nitrogen here from your products. You would just have, when you substitute N times HF, your HF would be 0 for N2. Same with over here in your reactants, you could have oxygen and nitrogen. When you sub in your HF, enthalpy of formation information for it, it'll cancel out and you'd see 0 there. Okay, so they went and grabbed, you have your 8 for CO2. They went and grabbed the enthalpy of formation from that table. You have for water 9, and then they grabbed their enthalpy of formation from that table, and then 1 for octane, and then the enthalpy of formation. Okay, solve, and we get our value. Okay, so that ends up being also the higher heating values, 47.891 megajoules per kilogram for that fuel. All right, so now we kind of did this already, but it's a better, more complete showing of it is the energy balance. See, so it's our COE, okay? So when we were doing this, we're kind of doing a limited COE, right? But we'll talk about it here. So the big two things is we switch to moles, okay, in the COE, and we switch, the other thing we have is enthalpy, so our H values. How do we get, so getting H, so getting our enthalpy, so get moles and getting our enthalpy. So that means we're going to use, if we're using moles to get total enthalpy, right, that means we have moles times H bar, okay, because that's per kilomole. Instead of per kilogram and having mass here, we use moles and do per kilomole because we have a chemical balance, so it's easier to work in moles, okay? All right, so conservation energy, so if we're steady state, our DE system dt is 0, so then we just have energy in is equal to energy out. That's what you see here, okay? We have it on rate form, okay? There's a dot here. Energy in, out, okay? Or non-rate is here also, okay? And the other thing they use is per kilomole of fuel, okay? So that's just saying, all right, if you wanted more heat, you just add in more moles of fuel, okay? So doing it on a per kilomole of fuel. So here is our, enthalpy reactions. We're just looking at, instead of mass times enthalpy, we're moles times enthalpy, okay? So right here, instead of mass, we have moles, and then we have enthalpy per unit mole. All right, the next big thing where people get mixed up in is we have this enthalpy. Instead of it just being one enthalpy term, we have 3 here, okay? And it's very important to understand the difference, and that's because we have the enthalpy of formation that we talked about, because we have to include that enthalpy from the energy from the reaction, that chemical energy, okay? So we have the enthalpy of formation, okay, has that subscript F, and that's where we get table 826, right? So that has that chemical energy in it, but it also has the sensible energy up to standard conditions. So it also has it to 25 degrees Celsius. That's what that little degree symbol is telling us. Okay, that is at 25 degrees Celsius. So it's the formation to 25 degrees Celsius. So it has some sensible energy in it to 25. Okay, this delta this is our sensible enthalpy. Okay, at whatever temperature, at the temperature. This one here is again at 25. What it's doing is taking our enthalpy from our book and subtracting off the reference condition of 25 because the enthalpy formation already includes it up to 25. In the back of our book, our tables for enthalpy have 0 enthalpy, not at 25 degrees Celsius. I don't remember, it might be 0 degrees Celsius. So this just subtracts off because the enthalpy of formation includes it up to 25. So we would be double counting enthalpy if we didn't subtract off. Okay, so that's why you see this. Okay. So this one is always, you're just grabbing the value at 25 degrees Celsius in the back of the book for that product. This one is at whatever temperature you're actually at the reactants or products. Okay.
So to summarize some of that notation, the bar above it means it's on a per mole or per kilomole basis, and the circle means that it's at the
reference condition.
Yeah. Okay.
Yeah. So here it is summarized for you right here. So enthalpy of formation, the bars are per kilomole. We have it at 25, 1 atmosphere, right? And then this one, this delta, is that sensible enthalpy in reference to 25, 1 atmosphere because of that subtracting off, okay? So this already includes some of that sensible enthalpy to 25. So we only want to have any amount above it, right? If our products were at 25, then this enthalpy would be at 25, and so would this one at 25 degrees Celsius. So that would just be 0. And we would just have the enthalpy of formation. There wouldn't be any sensible enthalpy, any energy, because let's say we're at 100 degrees Celsius. Now, this is at 100. This is still at 25 because now we have this sensible enthalpy above 25 degrees Celsius. And then this one's at 25. All right. This is just moving stuff around. It's still the same conservation energy we see right here. They're just saying, oh, this is the total enthalpy of the products. This is the total enthalpy of the reactants, and you can see it. That's just this term right here, and this one is just right here. They're just moving stuff around. Okay. If we talked about the enthalpy of combustion, if you had the enthalpy of combustion reaction, that's just takes all that HF values out and combines it all into there. And then you just have the sensible energy change. Okay, any temperature that's different than that 25, right? We always were at 25 because we didn't talk about any sensible energy above that reference condition. We were always at 25 so far, right? So that's really, this portion right here is really that portion above that 25. Okay. So if you don't have any work, that term goes out and you're left with this, or here, no work, and you get down to this equation. All right, so closed systems, instead of having UF values, because we have H enthalpy of reaction values, instead of also tabulating like an enthalpy of formation for internal energy, since we're looking at closed system with change in internal energy of products minus reactants, we use the definition of enthalpy, which enthalpy is U plus PV. So we just rearrange for internal energy, and that's what you see up here. Okay, it's just rearranged for internal energy. Since we already have how to understand enthalpy, we already went through it, then all we have to do for closed systems is just subtract off PV. Okay, and that's what you see down here is, they're rearranging the definition of enthalpy. So then you just have U, and we already have all the enthalpies, the formation, the sensible. Then you just have this new term PV to subtract off. And it actually ends up being nice in that is the PV term, if you have a solid or a liquid, let's say a reactant is a solid, say carbon, a solid coal, then it's negligible because your PV is the same as pressure over density. So if you have solid or liquid, your density is high, so it makes that term very small, so you can neglect it. If you're an ideal gas, PV is RUT, so this is the bar in PV. So you just substitute it in for PV, or the universal gas constant times this temperature that you're at, so for the reactants or the products. All right, adiabatic flame temperature, okay? That's saying now we're insulated, so the energy is not being released out of the combustion chamber. So we've well insulated that there's negligible heat being released from it. And what that does is the only place for that energy to go then goes into the products. It goes into raising the temperature of the products. If you can't have any heat leaving that combustion chamber, that means that energy has to go somewhere from the reaction, and it goes into the temperature of the products. It goes into raising that sensible energy of the products. So we just canceled the Q. There's no work, no heat, so all you have is these two terms now. So the only place for that energy to go from the combustion is into raising the sensible energy of the product. So it goes into this enthalpy, because this is standard condition. This is at a standard condition. You know what you're coming in with your reactants here. So this is standard, standard, and then you know what your reactants are coming in, typically at those standard conditions. So the only place for that chemical energy to go into goes into raising that enthalpy for each of those products terms. And that's an important kind of distinction, because that actually tells us what the adiabatic flame temperature, the highest temperature a flame can be is the adiabatic flame temperature. So, you're burning a candle at home, the adiabatic flame temperature of that candle is the highest temperature that candle can be. Or the flame temperature of gasoline, adiabatic flame temperature is the highest temperature that flame can be of gasoline. Okay, so that's the max that we can have the products, the combustion temperature be, is when we lose no heat. Okay. So what does this adiabatic flame temperature depend upon? Right? It depends upon the state of the reactant. So what temperature coming in here with, right? That'll play a role. It also depends upon how complete your reaction is, okay, and the amount of air used. So that's one thing that's used in combustion, is just adding more air. Okay, so if we add more air, that means there's more oxygen in the products. So there's more oxygen to absorb that energy released from combustion. So it actually drops your adiabatic flame temperature, drops your temperature of combustion. And that's used a lot, let's say exhaust gas recirculation in automobiles, or just adding more air in gas turbines to lower the combustion temperature, to lower the oxides of nitrogen emissions, to decrease certain emissions. That's important for. Okay, but the adiabatic flame again is its maximum value. Enthalpy. So I'll go kind of quick on this. We won't really do examples other than maybe in the slide. There's one or two. But if we just did the entropy balance on a reacting system, you end up actually, whether it's a closed system or a steady flow system, you end up with this equation. If it was a closed system, there's no, enthalpy crossing or boundary other than heat over temperature here. And you would have Sgen, and then you'd have the change in S of your system would just be products minus reactants. If it was an open system, then you have enthalpy being carried in or out, right? So that could be products and reactants coming in, products going out. But this is the SDT, and if it's steady state, now that side goes to zero, and you're still left with products minus reactants, because that's what's crossing in and out. Okay, so you actually end up with the same equation, whether it's a closed system or a steady flow system. And if you look at that, one key thing is if it was adiabatic, this reaction, then the product's entropy better be higher than the reactants, right? Or it's equal to zero for reversible adiabatic, because Sgen is zero for reversible and positive. So that means the entropy of the products better be greater than the reactants for an actual reaction to occur. That's one limitation. Okay. If we computing the actually entropy of a component, this is chapter 13. It's just showing you it again. All right, so one thing is second law analysis of reaction systems. So if we brought in exergy destruction, T naught Sgen. If we brought in, the other is reversible work. So way back in chapter 8, if we brought in reversible work, so X destroyed to zero, we have heat only crossing at surrounding the zero, so then the heat exergy from heat is zero. We get this. So that means for a reacting system, if we calculate this, we get the amount of work we can get. So if you're combusting fuel in your engine, that's the amount of max work you can get from it, from combustion. If you're combusting fuel in a gas turbine, that's the amount of max work. We can also simplify what you have here to the Gibbs function, which we saw in chapter 12, which just has this enthalpy minus Ts. So it simplifies what's there. So it makes it a nice, simpler equation when it just deals with this Gibbs and you know, the Gibbs already includes that TS in it. All right, if everything is at 25 degrees Celsius, that cancels these things, and you get this simple equation right here, okay? So that would be our reversible work, the kind of 25 degrees Celsius in, out, our max reversible work. Quick example is just reversible work. So again, that's our max work we can get. We have carbon, 77 degrees Fahrenheit. That's our 25 degrees Celsius standard for, but that's our standard for English units. We have 1 pound mole of oxygen. We're forming CO2. Again, it's to that standard condition, so we're in and out at the standard conditions. So that means they're just going to use this one because it doesn't have, you know, this that's above that reference temperature. All right, so reactants minus products, go and get our Gibbs for each of these. Carbon is 0, oxygen is 0. So we only have the Gibbs value from, and then this is again in the table in the back. Okay, so take a look at those tables and understand how to get your values for enthalpies and Gibbs. So we get that, plug it in, and we see this is the most work we could get from this chemical reaction. The reversible work, the maximum useful work just by combusting CO2 from carbon and oxygen. That's the max we can get. All right. So that's chapter 15. Okay, so we'll do examples next class. Okay. Sorry, I ran a few minutes over, just so then we can dedicate the whole next class to examples and not have to go back to the lecture slides. All right. If there's any questions, let me know. If not, I'll see you next class.
All right. Thank you.